Okay, so this is Rolle's theorem that probably you already know it from your calculus course. I don't want to prove it, but let us just talk a little bit about intuition behind that. So if you have a function which is defined on a closed interval a and b, and it is continuous on the closed interval and differentiable on the open interval from a and b, and more importantly, f of a is equal to f of b, then there exists an element c in the open interval a and b for which the derivative is 0. Okay, so the proof is a little bit, I mean, it's not hard, but it's a little bit convoluted. I mean, it's very simple, by the way, but we don't have time for it, okay? But intuitively, it should make sense to you. And can you describe it intuitively why it is correct? So, if you want to understand it, you have a closed interval on which your function f is defined, but in a continuous and differentiable manner, okay? But the point is that f of a, if this is a and if this is b, f of a and f of b are equal. So it means that at the end points you are at the same height. That's the meaning. So for example, if f of a is here, f of b should also be here. So you start from anywhere on this, solid line. You end anywhere on this solid line, but in a continuous and differentiable manner. Okay? So for example, I can start from here and move continuously and differentiable, and for example, end here. Okay? So the theorem guarantees the existence of at least one element in the open intervals for which the derivative is 0. So in this picture that I drew, how many of those points you see? You can see one of them here. You can see another one here. Okay? Why the f prime of c is 0? Because this derivative, this is horizontal, and this one is also horizontal. So there is no way for you, anyway, if you want to go in a differentiable and continuous manner, then you have at least to pass through a point for which the derivative is 0. Okay? Why differentiability is needed? Can I skip the consequence if I relax differentiability? Can I? So what is the difficulty? So if I want to go in a differentiable way, in a non-differentiable way, of course I can start from here and go, oh sorry, that is my mistake. That was a very stupid mistake for this, because I have to return back to the same height. So don't do that, this is the correct. Okay? Oh, sorry. I have to start with, yeah, that was very, very stupid. So I have to start with this height and go back to the same height in a differentiable and continuous manner, okay? So then it means that one point, at least one point, I can have 2 bumps or 3 bumps, okay? At least I have one bump, either upside or I don't know, I can have a valley as well. I can have a valley, I can have a bump. So it means that at some point the tangent line is horizontal. But if I do not want to respect differentiability, I can do it in this way. I can go here and I can return back. Yes? And then you see there is no point of that property, because I use this sharp point to return back to the same height, and I am avoiding to have a derivative to be 0, because the derivative of this function is nowhere equal to 0. So both of them should be in place in order the result to hold. Okay? Any questions? Okay, so this is also an extremely important theorem, and you have seen it in the calculus course, the mean value theorem. Usually I should mention it mean value theorem for derivatives, because there is another mean value theorem for integrals. Okay, if you have time today, we will go through it. Okay, this is the case. What does it mean intuitively? It means that if again I have a function which is continuous on the closed interval and differentiable on the open interval, okay, then you can guarantee the existence of a number C in the open interval such that f of the end point minus f of the initial point divided by b minus a is equal to f prime of C. Okay? So because you have seen this before, so let us go a little bit faster. But what is the intuition behind that? The proof is not very hard. I have written all the proofs in the notes. If you're interested, you can read it. But intuitively, what does it mean? So this means that if this is point A and B, and I don't know, let us say that here is f of A. So, and then let us say that here is f of B. Okay, so if I take this point and connect it to this point as a straight line segment, what is the slope of this line? Do you agree that f of b minus f of a, the difference between y coordinates divided by the difference between x coordinates, is the slope, the k value of this line? Okay? But let us say that now my function is continuous and differentiable. So this means that I have to somehow go in a differentiable and continuous manner from this point to somewhere this point. So I do not have sharp points. I cannot lift my pen and put it somewhere else because of continuity. So for example, let us say I draw it like this. Any way that you want to draw it. So then you can see that at least at one point here, for example, if I can convince you more or less, this is one of those points claimed by the theorem. Why? Because if I draw a tangent line here, what is the slope of the tangent line? It is f prime of C. So the k value of the slope is k prime of C. And then you see that this line turns out to be parallel to my line. So the slope should be equal. So it means that if I just connect the final points, the end points by straight line, I get some slope. And I can always find at least one point on the graph of my function so that the tangent line there is parallel to this line. That's the meaning of mean value theorem. But of course, in this picture that I have drawn, this one is one of them, this one is another one. But at least one of them is guaranteed. For example, if I just go simply like this, then there will be only one point, yes? So around here. Yes? But anyway, how you do it, if you respect continuity and differentiability, then you definitely get at least one point in the open interval where the slope of the tangent line and the slope of this line are the same. That's the geometrical interpretation of the mean value theorem. Is that understandable? Okay. But this is one of the most important theorems. So let us, for example, use this theorem to prove this inequality. So these are some applications. I have given you more examples in the notes. Please study them. Let us try to solve this problem together. If x1 and x2 are real numbers, I want to prove for you that the absolute value of the difference of signs of those numbers is less than or equal to the absolute value of the difference of those numbers. So how do you think we will solve the problem? For example, if I give this to you in the exam, I will tell you, use the mean value theorem to prove it. So you know somehow it is related to the mean value theorem. Okay, so how can we prove this theorem? This problem, 13.11. So in order to use the mean value theorem, I need a function. So that is something you need to guess, but that is extremely easy to guess. Which function do you guess that is suitable for this purpose if we are supposed to use mean value theorem to solve it? Which function? What? Sine function. So I would say that f of x be sine x. Okay, by the way, this if x, this is the best way to start. I would say if x1 equals to x2, we are done. But you write it in the exam. What does it mean? Why this is done? Because if x1 and x2 are the same, the left hand side is 0, the right hand side is 0, so we have the inequality. So I would say let x1 not be equal to x2. I don't know, without loss of generality, we assume that x1 is less than x2. It doesn't matter. Whatever I say, you can just reverse x1 and x2 and you can say the same thing. So if x1 is equal to x2, we are done. If they are not equal, one of them is less than the other one. Let us assume that x1 is less than x2. By the way, there is no difference because absolute value has symmetry. Okay? Okay, now what we do? Now it is time to introduce my function. I would say let f of x be equals to sine x. F is continuous everywhere. Sine x is continuous everywhere, also including this interval. Do you agree? Because sine x is continuous everywhere, including this closed interval. F is differentiable everywhere, including the open interval. Okay? Do you agree with what I'm writing now? Okay. So now, mean value theorem guarantees what? Can you write something for me? I have a function which is continuous on this closed interval. What is x1 and x2? x1 and x2 are the ones that I chose from the beginning. Okay? So, and I know that this function is differentiable on this open interval. So according to mean value theorem, the existence of a C where in the open interval x and x2 is guaranteed such that f of the endpoint minus f of the initial point divided by the endpoint minus the initial point is equal to the derivative at this point. That's just the mean value theorem. But let us adapt it to the function. So this means that instead of the denominator, I copy and paste it, nothing I can do. But instead of f of x2, I can write something. I can write sine x2. Because f of x is this one introduced by myself. And then this one is sine x1. But what can I write on the right side? F prime of c. I have to differentiate my function. And hopefully you remember this level. If this is more than this, I will give you in the problem. For example, if you're supposed to differentiate an arcsine function, I will give you the derivative. But for sine and cosine and the small, simple ones, I take it for granted. Okay? So this becomes cosine x. This is f prime of x, but I don't want f prime of x. I want f prime of c, so this becomes cosine c. Do you agree? Okay. This is already very similar to what I want to prove. At least the structure seems similar. But I do not have absolute values here. Okay, I put this. If this number is equal to this number, of course the absolute values are also the same. No, this is x2. Do you agree with what I am doing? If you tell me this number is equal to this one, I am allowed to conclude this. I am not allowed to go back, but I don't care. I'm going in that direction. Yes? So if two numbers are equal, absolute values are also equal. But now, the absolute value of a fraction is equal to the absolute value of the numerator minus the absolute value of the, divided by the absolute value of the denominator. Absolute value of cosine of c, you see I don't have any control over c. because the theorem only guarantees the existence of C. It doesn't tell me anything about C. But here I don't care. You know why? Because cosine, absolute value cosine, is always less than or equal to 1, no matter what C is. So this means that this is also less than or equal to 1. Okay, and this is my inequality. Yes, and the absolute value, in the absolute value you can change them, nothing changes, so it becomes exactly that way. So this is one of the applications of the mean value theorem that I think you need to know. Okay, any questions? This is an exam question. Let us solve that one as well. But I don't know. They have asked you formulate and prove the mean value theorem, but I promise you, don't ask you to prove any theorems. Okay, so that is gone. You can, if you want to see, you can see the proof in my notes. But let us do the second one. But the second one, to be honest, is a harder one, because in the first one, if you already have it in your memory, you can write it down. But for the second one, you have to be a little bit more creative. Okay? So, read the question so that I can start writing it here. So, formulate and prove the mean value. Formulation is that one. But the proof, you can see it in the notes. It's not very hard at all. But now we want to solve part B. Show that there cannot exist any function such that f prime of 0 is 0 and f prime of x is greater than or equal to 1 for all x non-zero x. Okay, so how is that? So just part B. So we want to show that this is not possible to artifact a function of this. I cannot have a function from R to R so that the derivative at 0 is 0, and for every x in R minus 0, the derivative becomes greater than or equal to 1. So we want to show it is impossible to have such a function. Okay, and then they are also giving you a hint, because in the first part they are asking you to formulate mean value theorem, so it means that the second part is somehow related to the first part. Okay, so how can we do that? So that's why I'm saying it's hard. So how we should start? So whenever you want to formulate your problem using mean value theorem, you need to have an interval and you need to have a function. Here you don't have any problems with your function. The function is supposed to be this f. But you need to have an interval. Okay, so I don't know. I would say let x be a positive number. Okay, and then consider these intervals. Okay, so I picked one x. I don't say what x is, but I'm just taking it positive. And using this positive x, I constructed two. Why I started with 0? Because it has something with 0 here. Okay, and then I am concentrating on these two intervals. Now my question for you is that, do you think if such a function exists, because we want to prove it does not exist, so we want to go for a contradiction. Okay, so let us assume that such a function exists. If such a function exists, then if such a function f exists, then f is continuous on and differentiable on. Okay, but in the exam you have to write why. Here we talked about it orally. Do you agree that this is the case? Why? Because in the assumption they are telling you the derivative at 0 exists, and when you say for every other x's the derivative is greater than or equal to 1, it means it exists so that it is greater than or equal to 1. So in other words, my function is differentiable everywhere. So you need to mention that because the function is differentiable everywhere, it is also continuous everywhere, because differentiability implies continuity. Okay, so now if my function is differentiable everywhere and continuous everywhere, of course it is continuous on this small part and it is differentiable on this small part. But you have to write this down in the exam, okay? So this means that this function meets the conditions of mean value theorem. Yes? So this means that, so therefore, mean value theorem, there exists a C in where? In my open interval 0 and x, such that what happens, f of x minus f of 0 divided by x minus 0 is equal to f prime of c. Do you agree?
But don't we just try and find like 1/2 with that, because f of x or f prime of x can't be less than 1 unless it's at 0, but at 0 it's 0. So then it's not continuous between 0 and 1.
You are talking about continuity of the derivative.
Oh, sorry. Yeah, no, sorry. Not.
We don't have any. We don't have the assumption about the continuity of the derivative.
Yes, but can't we formulate the with the mean value theorem so that we try to find the f prime of c equals 1/2, for example?
Yes, if you can, be my guest.
Yeah, but doesn't that disprove b? Because it,
No, but how do you know the existence of such a number that f prime of c, from here f prime of c is 1/2?
because we know that 0 exists within the interval.
Yes.
We know that any not like there exists.
No, you are talking about mean intermediate value theorem.
Oh, sorry. Okay.
But intermediate value theorem is granted if the function is continuous.
Oh, okay.
Okay? So we don't know if the derivative is continuous. We know f is differentiable, but we don't know if the derivative is continuous. By the way, do you remember we had an example that the function was differentiable and continuous everywhere, but the derivative was not continuous. So don't take it for granted. Okay, so, but do you agree with what I have written here? Be careful, this x is an arbitrary x. I just picked one positive number. For that x, we have this one. Do you agree? Okay, now this one is greater than or equal to 1. Why is that? Because x is positive. So this c is in this interval, so it is not 0, because it is in this interval. And if x is not 0, then f prime of any number is greater than or equal to 1. Is that right? Now, this is valid for every positive x. If I have a function, so you can call this function g of x. So what we proved that for every positive x, g of x is greater than or equal to 1. This is what we proved. I called this function, whatever it is, I called it g of x. Yes? X is positive, I chose that positive number, and I proved that this combination for any x is greater than or equal to 1.
You mean the whole fraction?
Yes.
Or just the...
No, I called the whole fraction g of x. Yes? And I'm saying that I was able to guarantee this one for you. Do you agree with me or not? Okay, if that is the case, then I take the limit from both sides and I send x to 0 from the right. If a function is greater than another function and the limits exist, then the limits will keep the order. Okay? But this, I have to convince the examiner that this limit exists. Otherwise, I cannot just take the limit. But why this limit exists? Why this g of x is a name I gave to this guy. So why this limit exists? Let me write it in this form. I am sending x to 0 from right. So what is the definition? Do you see this is the definition of the derivative? So this is the derivative at 0 from the right. Okay? So this means that this exists. But because the function is differentiable, it doesn't matter if you are looking at the right derivative or the left derivative. It becomes equal to the derivative as well. Okay, so this limit exists. If you want, you can write it like this. So this means that f prime positive 0 is greater than or equal to, oops. Oh, yes. It's greater than or equal to 1. Yes? But f prime positive 0 is the same as f prime of 0. Can you see the contradiction now? Because f prime of 0 were supposed to be 0. But f prime of 0 is also greater than 1. So 0 is equal to that, and is greater than 1. So of course we cannot live with this contradiction. Yes? So that's why I'm saying this is harder than the first one. But that's the good news as well, because that contains only 1 point, okay? Anyway, hopefully you could follow what I said. Let me see what is left here. So this is very probably small, you cannot see it properly, but this is already, you know, that's the definition of increasing and decreasing functions, yes? So what is that intuitively? If when I go to the right, if the function goes up, the function is increasing, but if it is constantly going up, I would say it is strictly increasing, but sometimes the function might go up and be level and then go up. So this function is increasing, not strictly increasing, because at some point it becomes horizontal. And if it is the other way around, the function is decreasing and strictly decreasing. And we have a name for it. It's called a monotone function. When I say that I have a monotone function, it means it is either increasing or decreasing. Yes? Okay. And of course, you have to work on intervals. Yeah, these are more precise definitions, but intuitively, that's the meaning. Okay, so I have talked about monotone and strictly monotone, so we skip this slide. And then this is a theorem. This probably you remember it from your calculus course. You remember, if the derivative is positive, if the derivative is non-negative on an interval, then f is increasing on that interval. But if the derivative is strictly positive on an interval, then f is strictly increasing on that interval. The proof is very, very simple. I want to skip the proof. You can read it in the notes yourself. But this is exactly what you learned in the calculus. Yes, it is easy to understand it because you have already seen it before. This one is an important one. By the way, it is not trivial. So high school students cannot prove this. Okay? In high school, you know that if a function is constant, in high school you can prove that the derivative is 0. Okay? But if the derivative is 0 on an interval, that is extremely important. Not just on any set. If the derivative is 0 on an interval, the function is also constant on that interval. Even though might be you know it from high school time, but it was not trivial. Okay? So now, why is that true? I want to prove this one using the mean value theorem. So, why this is true? How should I prove that a function is constant? So, let us say that f, okay, and I know that for all x in I, f prime of x is 0. My claim is that f of x is a constant. So let me write constant on that interval. So what is the meaning of f is constant on that interval? It means that there exists a c in R such that for all x in that interval, f of x is equal to that constant. That's the mean. That's the translation of a function being constant. Okay, how can I prove that? So let us imagine this scenario. For example, let me consider this I. Okay, and I want to show that my function under this condition is constant. What does it mean? It means that any 2 points that you choose, if they are not the same, f of x1 is equal to f of x2. That's the meaning of being constant. It means that no matter which pair you choose, even if x1 is not equal to x2, but f of x1 is equal to f of x2. That means that this function is constant. But then, it is very simple. F is continuous on x1 and x2. Do you buy it? Yes, because f prime of x equals to 0 on the whole interval. What does it mean? It means the function is differentiable on the whole interval, which is equal to 0. So this means that if you make this one smaller, of course, that is also differentiable there. And if it is differentiable, it is continuous there. So f is differentiable on this one. Yes? Because it is differentiable on the bigger one, so it is differentiable on the small one. So by mean value theorem, what can I conclude? I can conclude there exists, I don't want to confuse it with this C, there exists a C where in x1 and x2, such that what happens? F of x2 minus f of x1 divided by x2 minus x1 is equal to f prime of C. Yes? But what is f prime of Kc? Kc is somewhere here. 0, because for every point in the bigger interval, the derivative is 0, including this one. So I have a fraction which is 0, so it means the numerator should be 0. And we are done. So it means that any 2 points that you choose, the values of the f values are the same. That's the meaning of being constant. So the proof was very simple, but it was not a high school problem because they didn't know about the mean value theorem. Okay? Okay, now let us go to an application here. I have given a harder one in the notes, but I knew that there will be no time, so I picked a simple one. So this is a very famous trigonometric identity. Okay, we want to show that this is equal to 1, sine squared x plus cosine squared x is equal to 1 by this theorem. So, and remember that if I give some question in the exam to prove some complicated thing is equal to a constant, this might be the trick. So what we do this. I would say let f of x be equals to sine x squared plus cosine x squared defined on an interval here, defined on minus infinity to infinity, which is of course the same as r. So r is also an interval because this theorem only works if your domain is an interval. Okay? If the domain is not an interval, it might be union of intervals. There might be you have different constants. One constant on one piece of interval and another constant. So you cannot say that the function in totality is constant. So let f be this defined on that. Yes. I take the derivative. Okay. By the way, what's the derivative? Can you help me? What is the derivative of sine x squared?
2 cosine.
2 goes down, so it becomes 2 sine x, but you have to multiply by the chain rule to the derivative of the base, which becomes cosine x. Yes? And this one the same. 2 goes down, but I have to multiply by the derivative of cosine, which is minus. So what is the answer? 0. Yes? So the answer is 0. What does it mean? The domain is an interval, the derivative is always 0. What does it mean? It means that f is constant on r by that theorem. But, so what does it mean? It means there exists a constant in r so that for all x in r, sine x squared plus cosine x squared is equal to c. That's the meaning. But I need more than that. I want to make sure that my constant is 1, not any constant. So, but that is easy. How should I do that? Yes?
Plug in a value.
A value that we know. Because if this is supposed to be constant, it means regardless of what value you choose for x, that constant is the same constant. So, for example, I put x equals to 0. Then what happens? This becomes sine of 0 squared plus cosine of 0 squared is equal to c. But then I know cosine of 0 is 1, sine of 0 is 0, so this means c is 1. Be careful the logic. I didn't find... First, I proved that this is a constant. So then it means that no matter which value I choose, it will give my constant. Okay? So then it means that I put them together and I have my formula. The one that I have solved it for you in the notes is this one. To prove that arctangent of x plus arctangent of 1 over x is pi over 2. So that's the same type of trick. So a function is given on the left, and then you are supposed to prove it. So, sorry, I have mentioned that x is positive because otherwise I am in trouble with integrals. So I have asked you to prove that when x is positive, this is the case. So what do? You define a function. If I give this in the exam, I will tell you the formulas for the derivative of arctangent. But I expect you to be able to derive this one yourself. Okay? Because that's a composition of functions. Chain rule. Any questions? So this was one of the important theorems. This is Darboux theorem, and that's the last thing we want to talk about. But I was thinking to go back a little bit to the integrals as well. So might be we have to postpone it for tomorrow to see how it goes tomorrow. This is a very important theorem, which is called Darboux's theorem. And this is, sometimes it is called intermediate value theorem for derivatives. This is what exactly you wanted to talk about. Okay? So then might be you can use this and that to combine them together. Okay? So, do you remember what was intermediate value theorem? Intermediate value theorem, we had it in the notes, but we didn't go through in the lessons. It was in the classroom notes. We didn't have time to go through it because you have already studied that in your calculus course. I just want to describe it because the proof is nice to see why this works, but at least the content is more important to understand. So the mean value theorem tells you that if you have a continuous function on a closed interval, for example, so here is A, here is B, and then let us say that I start from somewhere and I go continuously, differentiability is not important, I go continuously and end somewhere here, for example, something like that. Okay, and then I look at the maximum and the minimum. Okay, so in this case, the minimum is here, the maximum is there. Okay, so if I do it continuously without lifting my pen and putting it somewhere else, it means that the graph of my function, actually, the function will take all the intermediate values. Yes? So if you pick any number here, lambda, which is between the minimum and the maximum, then there exists at least one c in the open interval a and b, such that f of c becomes that lambda. That is the intermediate value theorem for continuous functions. Okay? In this case, how many of them I have? I have a lot of them actually. Yes? Because if I go backward, this is one of them that goes to lambda. This is another one that goes to lambda. This is another one that goes to lambda. But at least one of them, the existence of one of them is guaranteed. This is the normal intermediate value theorem that you learn. Now we want to say something similar, and that is called the intermediate value theorem for derivatives, or Darboux's theorem. This tells me that if I have a function from I to R, okay, and it is differentiable on I, okay, and then what do I have? For example, let us say that this is my I, and then I have 2 points here and there. For example, A is less than B, as I have written there. And then what I know that this function, so when I say this function is differentiable on I, so it means f prime of A is a number. And I know that f prime B is also a number. But which one is greater than the other one, we don't know. But they are not, assume that they are not equal. Okay? If they are not equal, and lambda is strictly between f prime of A and f prime of B, then again, like intermediate value theorem, but for derivatives, there exists a C in the open interval of A and B such that the derivative at C is lambda. So what does it mean? It means that if you have a number strictly between 2 values of the derivative, that value will be attained by your derivative at some point between the points. So it's exactly like intermediate value theorem, but for derivatives. Is that right? Okay, so that is the intermediate value theorem. So let us see if we can cover this one as well. This is also good to read. So Darbow's theorem says that the derivatives have the intermediate value property, even though they need not be continuous. That's extremely important. We have already seen examples such as the derivative of x squared sine 1 over x of differentiable functions whose derivatives are not continuous. Darbow's theorem says that no matter how badly a derivative behaves, it cannot jump. Okay? So, if f prime takes the values alpha and beta, it must also take every value strictly between them somewhere in between. So that is the essence of Darbow's theorem. Okay? And let us see if I can manage to solve this one as well. Show that there is no differentiable function such that this happens. So let me formulate it a little bit better. So I want to say that it is not possible to look for a function defined on R and real valued so that if x is positive, the derivative becomes 1. If x is negative, the derivative becomes minus 1. Okay? So you see, I am claiming that you cannot find any differentiable function with these 2 properties. It doesn't mean that f prime of 0 is not defined. Yes, it is defined because I am assuming that my function is differentiable everywhere. I haven't talked anything about f prime of 0, but I am telling you that for positive ones, I demand that the derivative should be 1. For negative ones, I demand the derivative should be negative. I want to prove that you cannot find a function with that property. You cannot find a function which is differentiable everywhere on R with these 2 properties added on top of it. Okay? So why is that true? So for example, we can say that so let me talk about a symmetric interval. So let me concentrate on this interval. So if I ask for contradiction, let us assume that such a function exists. If such a function exists, it means that its derivative at 0 is a number. So let me call it alpha. Okay? So let me call alpha to be f of 0. Okay, and then if I ask you what is f prime of minus 2, I'm just randomly choosing, you will see why it works. According to this one, it should be negative 1. What is f prime of 2? It is 1. So it means that for every lambda that I choose between these 2 numbers, for every lambda, according to Darbow's theorem, so this is Darbow's theorem, there exists a C corresponding to this lambda, where in this interval from minus 2 and 2, such that f prime at c lambda is equal to lambda. Do you agree with what I have written? So if such a function exists, I call the derivative at 0 alpha, and I calculated randomly, but of course I had some ideas why. F prime of -2 is -1, f prime of 2 is 1. So it means that if I choose any number between these two derivative values, which is -1 and 1, according to Darbo's theorem, I can find the C lambda in the interval from -2 to 2 so that this happens. Okay? But can you see the contradiction now? Can you see the contradiction? Because what are the possible values for f prime of C lambda? I don't know where. So what are the possible values? If C lambda is somewhere here. If C lambda is negative, so this means f prime of C lambda should be -1. If C lambda is positive, so this means f prime of C lambda should be 1. And if C lambda happens to be 0, f prime of C lambda should be alpha. Yes? Alpha. So, but lambda cannot be this one because lambda belongs to -1 and 1, so this is ruled out. This is also ruled out because lambda is in this interval. So this is the only option. So this means that if C lambda, so what is the contradiction now? Can you see the contradiction? If f prime of C lambda is that one, so what's the contradiction? Because this is working for every lambda. So can you see the contradiction now? Yeah. F prime of C lambda is alpha. So it means probably we have infinitely, because there are infinitely many elements here, but the output values is only alpha. So then it means that I can, okay, so I'm confused now. This should be extremely simple now. Can you see that? Just 1 minute and we are finished. So lambda, for every lambda here, I have f prime of C lambda is equal to lambda. So it means that if I choose 1/2, for example, there will be 1 for, okay, so might be that is the reason, yes? Because for every lambda chosen from here, there should be some, okay, so let me choose my lambda to be 1/2. Yes? Let us choose 1/2 here. Then f prime of a number is supposed to be 1/2. Can it be the case? It might be the case if I am so unfortunate that alpha is 1/2. But if alpha is 1/2, then choose 1/3. So that is the contradiction. Is that clear? Because this is ruled out, this is ruled out. Alpha is a number. If I choose 1/2, I know f prime of 1/2 because 1/2 is positive. It becomes 1. Yes. And if I am so unlucky that alpha is 1, I change my number. Okay, because at most it can cover one number for me. If I change my number, it cannot cover everything. And there are uncountably infinite numbers here. So definitely I can find a number that does not work. Okay, so that's good. Thank you very much.